Pat and Jean have got a problem to solve in their workspace. They're trying to move a 20-gallon pail up onto the table so that they can siphon liquid out of the pail into another pail. They've tried lifting it before. It's heavy and awkward, and it tends to spill or slosh around. So moving it without spilling or sloshing around and mixing up the material that's in the pail is one of their objectives. So they're going to try this pulley system that they've thought up, because Pat observed that pulling sideways on a line can tension that line a lot more than the side pull force. So Pat thinks that by pulling down on a line that's stretching across the ceiling like this, they can get the bucket to go up without having to pull with the full weight of the bucket on this line over here. And then Jean over here, once the bucket gets up there, can pull it sideways, and they can set it down gently onto the table. With a little luck, this will all go smoothly. They can do everything slowly and with low enough loads that things will work out. Before they try this, being good engineering geeks, they're going to try to figure out what the forces are going to be that they need to apply here. In order to do that, we need to know something about the geometry in this system. So, important elements of geometry, well, obviously the angles that these lines are at matter, because if they're pulling straight up and down, then Pat's going to have to pull quite hard. So let's call this theta 1, and that's theta 2. Now, what do we know about theta 1 and theta 2? Well, if Pat's pulling straight down, then this pulley is going to move so that theta 1 and theta 2 are equal. Right? If it was way over to the side here, Pat would either have to pull this way to keep it over to the side, or Pat would have to move over towards the middle so that theta 1 and theta 2 were the same. Likewise, if Pat was over this way, Pat would have to pull this way or move towards the center. So if Pat's going to pull straight down, theta 1 is equal to theta 2. Or let's say approximately equal to theta 2. And they're both equal to theta. So it's pretty close. Now, the other thing that's going to be important that tells us how hard Pat is going to have to pull, this force applied by Pat downwards on the rope, is going to be what the tension is in the line. Now, the tension in the line, how hard the line is being pulled or stretched, it might not be the same in every location. This section might have tension T1, that one T2, and this one T3. And they might be different. In fact, if the pail is going to go up, then T2 has to be bigger than T3 to overcome the friction in this pulley. And in order for the line to roll through this pulley, as Pat's pulling down, because there's going to be more line over here the further Pat pulls down, so the line is moving that way through the pulley, T1 has to be bigger than T2 to pull it through the pulley and overcome the friction in this pulley. So in fact, T1 is going to be greater than T2, which is going to be greater than T3. That really complicates the problem because we don't know exactly what goes on with the friction in these pulleys. But we know it's pretty small if we've gone out and bought good quality pulleys. So let's assume that T1 is approximately equal to T2, is approximately equal to T3, which they're all equal to T. That's not true, but it's pretty close to being true. And T, what does T have to be equal to? Well, if the bucket's going to go up slowly, then the tension in the line has to be enough to offset the weight of the bucket. The force due to gravity pulling the bucket down. So T must be about equal to the weight of the bucket. So now we've defined our problem, we've got some of the details figured out here, and we've figured out what approximations we're going to make. Now we can apply a basic force balance to figure out how much force Pat has to pull with in order to make that 20-gallon bucket start to lift. And we're going to assume that everything's happening slowly here, so Pat doesn't have to apply any extra force, or much extra force, for the acceleration of the bucket as it goes from having zero velocity to having a very small velocity on its upward journey. So if we look at a force balance right here at this pulley, we've got T2 pulling off in that direction. We've got T1 pulling off in that direction. And we've got Pat exerting a force down in this direction. That's all that's happening on this block in here. There's our free body diagram. That's the body. And those are the things that are acting on it, on the pulley. Now we know about the angles that these tension elements go off at. We know that this is going straight down. So we can do a force balance in the y direction and say that the sum of the forces acting in the y direction is approximately equal to 0, since the bucket is moving slowly. The acceleration is approximately equal to 0. Sum of the forces in the y direction. Well, T1 and T2 each have components pulling up in the vertical direction. So there's a theta 1, theta 2 angle here. And the force in the vertical direction, if we call this our y direction, the force in the vertical direction from T1 is T1 times sine theta 1. And the force from number 2 is T2 sine theta 2. Whoops, no equal sign there. Those are adding together. That's a plus. T1 sine theta 1 off in that direction. T2 sine theta 2 for the force off in that direction, but the components acting vertically. Minus, in the negative y direction, we have Fp. And all of that equal to 0. Well, T1 and T2 are both equal to each other, and they're equal to T. And in fact, that T is going to be W, the weight of the bucket. Theta 1 and theta 2 are both pretty much equal to each other, and that's going to be theta, the angle in here. So if we rearrange that, we can wind up with T sine theta plus T sine theta, so that's 2 times T sine theta, equal to Fp. Right? There's negative sign going across to the other side of the equation. Now 2 T sine theta, T is equal to W, so Fp will be equal to 2W sine theta. What that tells us is if we make theta small, then Fp will be small. If we make theta large, then Fp will be large. If theta was 90 degrees, if this was all collapsed in like this so that the T1 and T2 were both vertical, then we'd need to actually lift with twice the weight of the bucket to get that to go up. Now we have a formula that tells us how the weight of the bucket is related to how hard Pat has to pull. But let's try to put some numbers to this by filling in something about the geometry here and the weight of the bucket. First off, let's try to make a reasonable estimate of the weight of the bucket. Now, if the bucket's filled with water, or something like water with a specific gravity close to 1, then the density is about 8 pounds. This is actually a specific weight because pounds is force. 8 pounds per US gallon, or about 10 pounds per imperial gallon. So we know this is a 20-gallon pail. I'm betting that the capacity of this pail is measured in US gallons because the US market's pretty dominant for anywhere that's still using gallons. So probably 8 pounds per US gallon times 20 gallons gives us about 160 pounds of water or water-like stuff that's in here. And suppose the bucket weighs about 4 pounds. That gives us W of around 164 pounds. If you don't like pounds and ounces and gallons that come in either US or imperial, and you'd prefer to work in metric, then we know that water weighs about 1 kilogram per liter, or 1,000 kilograms per cubic meter. There's only 1 liter, so we don't have an imperial or a US to worry about. And the bucket we're just making a guess here, so let's stick with round numbers. Let's say it's about the same. It's about 2 kilos is the weight of the bucket. So the end result of that is that the total mass we've got, oh, we need to know how many liters in a gallon if we know this is a 20-gallon pail. Well, there's about 4 liters in a US gallon. So about 4 liters per gallon. That's not strictly true, but it's close. Gives us 4 times 20 is 80 kilos of water and 2 kilos of bucket. 82 kilograms times acceleration 9.81 meters per second squared. Rounding off for the slightly less than 10 there, this gives us a number W approximately equal to 800 newtons. So you can either have your force in pounds or you can have your force in newtons. Both of those are about the same thing. They differ by a factor of about 5. Now, if that's our W, then what's theta? Well, if we're going to start off and get the best mechanical advantage we can, we'd like to set this up with the rope tight right across there between this point and the pulley, so that initially theta is going to be equal to 0. If theta is equal to 0, then no matter what W is, FP is going to be 2W sine theta. Sine theta is 0. FP equals 0. Initially, it's really easy to pull that line sideways. But also, pulling it sideways results in hardly any motion of the pail going upwards. So yes, you've got a huge mechanical advantage, but you pull quite a distance before the pail moves even just a small amount. But you can take the weight off that pail quite easily just by pulling a little bit sideways, supposing you want to slip another pallet in there or you want to slide a cart underneath it. Now, as we pull down, as Pat's pulling down on this rope, theta is going to increase. And in the drawing we've done, it looks like theta's gotten up to about 30 degrees. But let's assume we make only a relatively small pull sideways. We've put our pulleys far enough apart that we can still get enough lift with a relatively small sideways pull. And let's suppose that our theta gets to a maximum of around 15 degrees. The sine of 15 degrees is 0.26, about a quarter. And as a result, in that case, FP will be about a quarter times 2 is about a half times the weight, gives us values, well, about 85 pounds. Or about 800 newtons divided by a little more than 2, or sorry, multiplied by a little more than a half, gives us about 420 newtons. So as long as Pat can pull down with a force of about 85 pounds, or about 420 newtons, whichever units you prefer and understand best when you're trying to lift a bucket like this, if Pat can pull down that hard, Pat can raise the bucket as far as getting to these angles being about 15 degrees. How high does that raise the bucket? I'll leave that as an exercise for you in the geometry of this system. It really depends on how far apart these two pulleys are.